All right, welcome everyone to the Decarbonization Study Town Hall. I'm Narit Katz. I'm the Chief Sustainability Officer for UCLA and one of the co-leads of the study. The presentation today will be mainly delivered by the study consultants, but I'm going to give a bit of background before we get into it. So this study is in support of UC and UCLA's climate goals or climate action. We all know that the climate crisis is very serious and that imminent action is needed. There's a clear consensus from scientists and researchers, including our own. So recently, the UC last year made a commitment to more aggressive climate goals that really focus on direct decarbonization. We have a long history of climate leadership with energy efficiency and a prior goal of carbon neutrality, but this new goal moves away from an offset-based strategy towards full transformation of our energy infrastructure. So in support of those goals, we received some funding from the state of California to conduct decarbonization studies on each of the campuses. And UCLA's study is underway, and we'll be sharing some of the progress today with you and hopefully answering any of your questions. Pictured here on the slide is UCLA's cogeneration plant. Some of you may be familiar, some of you might not. This is the sort of beating heart of the energy of the campus. The cogeneration plant has been in operation for a few decades, and when it was built was incredibly innovative, and it's been one of our biggest assets in terms of sustainability because it's highly efficient. For the decades it's been operating, it was able to produce electricity for UCLA at less than half of the emissions of the grid. Now, as the grid moves towards renewable energy, that advantage from an emissions standpoint is decreasing. And long-term, if we want to get to full decarbonization, the cogen is now our biggest challenge in terms of on-site Scope 1 emissions. And so the focus of this project is developing scenarios that will help us get to the UC target of reducing Scope 1 carbon emissions by 90%. And we will be evaluating how close we can get to 100%. And to really look for the quickest pathway or what timelines are feasible. And so the consultants will be walking you through what that process is so far, what some of the scenarios are, but the outcomes of this study in terms of the scenarios and the analysis will be shared with UCLA leadership and will be used to develop a path forward and an updated climate action plan in the year that follows the study. The study will be completed by July and submitted to UCOP. Next slide. So there are 5 sections or deliverables for this study. The first, as I mentioned, is the strategy to achieve 90% reduction. And so that will be a number of different highly technical scenarios. UCLA has one of the most challenging infrastructures to transform. We are a highly dense urban campus, and we are also the only campus that is integrated with our medical facility. So the resilience that the cogeneration plant has provided is critically important on any campus, but particularly on our campus with our medical facilities, our hospital. So currently, the current power plant that we have has the ability to what's called island. We have a microgrid for the campus, and if there is an outage in an earthquake or similar situation, the cogen plant is able to stay online even when the city around it is dark. And that was actually tested in the 1994 Northridge earthquake, not on purpose. So that resilience is critical, and part of what this study will look at is what are alternatives? How can we retain some of that reliability, but also chart a pathway forward to cleaner energy? All of this energy transformation will have a significant cost to it, or at least an investment long-term. It may have significant cost savings as well, but there's no getting there without significant investment. So deliverable 2 of the study is a cost analysis that will look at the full life cycle cost of these projects, the operational cost, as well as the capital investment. We expect that this will be in the order of $1 billion to $1.5 billion, but that portion of the study is still underway. But given what investments have required in other situations, other campuses, we expect that to be the order of magnitude. Deliverable 3 is climate justice and equity. As you'll see later in this presentation, equity is also part of how we're assessing all the scenarios, but it is really important, and so it has its own standalone deliverable for the study as well. I think many people on this call know that climate change is not equitably felt in either its the benefits of the transition or the negative impacts of climate change. Both are not equally distributed as things stand now. Many wealthier nations and wealthier individuals contribute a larger proportion to the emissions that cause climate change, but the effects of the problems that we're seeing right now in our state, in our city, from extreme heat to wildfires to increased intensity of storms, the negative consequences of those are often felt by Black and Brown communities, by the Global South disproportionately, as well as by more vulnerable communities. And so this section of the study will be looking at those impacts in the context of UCLA and our region, thinking about who our vulnerable communities are, as well as thinking about what is called a just transition, which means as you're transitioning infrastructure and moving to renewable energy, how are you making sure that the workforce is transitioning as well, and thinking about economic and job impacts. So our consultants have a sub-consultant with experience in community and climate justice work that is supporting that work. And then deliverable 4 will say, okay, we have this study. What else do we need to really fully complete our climate action plan? This study focuses on scope 1 emissions. For anyone not familiar with that, that means direct combustion of fossil fuels on the site, in this case, the UCLA campus. Scope 2 is purchased electricity for us, and scope 3 is everything else, indirect emissions. And so that's commutes and air travel currently is what we're measuring, but scope 3 can include things like emissions from waste and supply chain, and there is a working group within UC looking at other forms of scope 3 emissions that could be tackled. So deliverable 4 is what are the gaps needed to do the rest of the planning. And then the final deliverable is about applied research and learning. So how do we integrate teaching and learning within the study? We have some great examples of that living laboratory approach at UCLA. For example, we have a solar microgrid on top of Structure 9 that was part of a major research project looking at vehicle to grid integration. And that successful research project led to more recently a commercial pilot of that type of work in Los Angeles. So as we invest in this major transition, we want to think about how that can also further our research and teaching goals. And so we've been having meetings with some faculty. We would love to hear from you if, as you watch this, you feel there's intersections with your teaching or research or classes. So my email is nkatz@fm.ucla.edu. I will put that in the chat as well. Our department email, sustainability@ucla.edu, also works, and we would love to hear from you. Next slide. So I'll be handing it to our consultants to talk about the process, but I want to make sure to just clarify for everyone 2 big points before we get into this. One is that I mentioned that the cogen is a significant piece of the puzzle, and so the scenarios you're going to see today, the way they're outlined on the slides, is really focused on that portion of the study, what happens with the main Westwood campus. But the scope of the study includes all of our properties that UCLA owns and operates. So that includes other off-campus hospitals, other facilities, even the new South Bay campus, downtown, et cetera. So that's all part of the scope of the study. I also want to make it clear that UCLA has been engaging in climate action for many years, energy efficiency through our Smart Buildings and Labs program, solar energy on site, and we have already existing plans to do more extensive solar at UCLA through the feed-in tariff program with LADWP. So these scenarios will all be on top of those existing initiatives or in addition to. So that's like the baseline that we're dealing with has some of that already. And then lastly, a lot of the questions we get on the study, since a lot of it is about electrification, are what is the electricity that will be used for those types of scenarios? UCLA has a target of 100% renewable energy procurement. So all of our electricity will be renewable by 2025, which is around the corner. So all of the electricity that would be feeding into this would be renewable. And with that, I'm going to hand it to Zach Stevens from our consulting firm, WSP, and he will walk us through the more technical portions. Feel free to put your questions in the chat, and we look forward to dialogue afterwards.
Awesome. Yeah, thanks, Nurit. So hello, everyone. I'm Zach Stevens, a vice president at WSP in our Built Ecology team, which is our sustainability group. And I am the technical analytics lead for the project. So we'll start by talking about the process and some of the solutions and scenarios that we've been mapping out as we try and wean our way down to a preferred decarbonization scenario. So this first graphic is an overview of the process, which Nurit talked about a little bit, but it began with phase one, which is what we call the reconnaissance phase. We spent a lot of time with Nurit and her team, both a decarbonization task force and a technical subcommittee, understanding the goals of UCLA, understanding what's important to the different stakeholders on campus, which fed into the criteria that we developed. We'll be talking about that, but those criteria are how we assess the different scenarios. So we have a multi-criteria decision-making framework that we're using to score all the different options that we have. We did a lot of document review and campus tours to understand existing UCLA campus infrastructure, namely the cogeneration facility, which is really a tri-generation facility because it's producing power, chilled water for cooling, and steam for heating in the facilities, as well as process steam for things like medical sterilization or labs that use steam directly. And then moving into phase two is our technical solution development. So based on our understanding of the goals and existing infrastructure and challenges and benefits, we started developing decarbonization measures and decarbonization scenarios to tackle those scope 1 emissions reductions goals. We came up with mechanical engineering concepts for various designs and equipment that we could use to meet that goal, as well as the electrical infrastructure to support it from an engineering perspective. And once we had those ideas kind of laid out and stress tested, and we made kind of a short list of scenarios, which as you'll see ended up being about 14 different scenarios, so maybe not so short. Then we moved into phase three, which is the decarbonization scenario modeling and assessment. So this is where we get to use that multi-criteria decision analysis framework. So that's the MCDA acronym to score all of those different scenarios and their various pros and cons relating to our key criteria, which we'll see later on in our presentation. So for each of those scenarios, we have a detailed carbon model, which is essentially an energy model where we're looking at the demand on campus, looking at real data from campus, as well as modeling how these different scenarios and the different equipment and systems we'd be deploying would handle the heating, cooling, and electrical demands on campus moving forward in that scenario. Understanding the energy that would be consumed, the cost of that energy, and the carbon emissions associated with that energy. So we end up with a energy, carbon, and cost model that feeds into our decarbonization scenario, what our emissions will be over the project period and beyond, as well as that cost benefit analysis. And we are working with a cost estimator to develop capital costs alongside those operating costs that come more directly out of the model. And then finally, in phase four, we're starting to, this is the next phase, hone in on that preferred scenario solution. So looking at the results of the MCDA, sharing the results with the broader UCLA community, and starting to make decisions on which of those scenarios are most beneficial and want to be put forward to be made into reality on campus. So that's the overall process. So let's get into our decarbonization scenarios. So little nomenclature here. When we talk about scenarios, those are those 14 kind of high-level scenarios that I mentioned. Those are built up of multiple decarbonization measures. So below is just kind of a generic example of things that are measures that might roll up into an ultimate scenario. As Narit mentioned, on-site PV solar arrays, that is happening in all of the scenarios, and really that addresses scope 2 emissions, so it doesn't have a big impact here, but that's just one example of a decarbonization measure. Other measures might be conversion of the cogeneration facility to another type of equipment that uses low carbon or zero carbon energy sources, or it could be more distributed solutions like converting the steam network to a more efficient hot water network on campus. Another really good example that is applied in all of our scenarios that we won't focus as much on, because as Narit said, there's a big focus on the cogen plant itself as the central campus infrastructure, but we are also including decarbonization of distributed assets, both on the Westwood campus and off campus. So converting boilers as they age out to highly efficient and all electric heat pumps, converting domestic hot water systems from gas to electricity as well. So that is a measure that is in all of our scenarios as an example, along with kind of the central infrastructure that we'll talk about in more detail. So like I said, there are 14 scenarios that are kind of grouped into 6 primary categories or scenario categories that are tied to really the central infrastructure for the main campus in each scenario. So we'll talk about those scenario categories next. But first, we start with our business as usual case, abbreviated as BAU, which is useful for comparison as we look at potential scenarios that are a wholesale change in how you're approaching energy production on campus. So as Narit mentioned, our business as usual is this highly effective and efficient cogen plant, which is taking natural gas provided from SoCalGas and producing electricity, chilled water, and steam. It also has a grid connection to the utility as backup. So if the cogen happened to go down, you've got backup grid power. If the grid goes down, you have the ability to island and produce and continue to produce electricity and heating and cooling to campus. So it's a pretty resilient system, but it is tied to natural gas, which is methane. And as you combust it, it produces emissions. So that's our existing system. So for comparison basis, for our model, we projected out what that business as usual case would be if we did nothing and continued to operate the campus for the next 25 or 30 years. What would it look like? And you would continue to see a gradual rise in emissions as the campus itself grows, and no real major reductions during that time. And we would not meet our 90% reduction target, which is that dashed red line there at the bottom. So that's our basis of comparison. For our first scenario category, we've got an all-electric central plant. So this would be essentially replacing that campus steam network with a hot water network that is fed by a new all-electric central plant. So this is kind of using very popular present-day technology for producing really efficiently hot water and chilled water. So there's some parts and pieces there, which would include heat recovery chillers to do simultaneous heating and cooling in a really efficient manner, air source heat pumps, as well as chillers and cooling towers for those really hot days. This is a system that we're very used to designing and is popular for new construction for large facilities and hospitals and things like that. So the benefits of this system are it's extremely energy efficient and has a low life cycle and supply chain equity impacts because the demand on the grid as far as an electrification scenarios go is about as low as you can get, because it's kind of best in class in terms of efficiency and electrical demand. It does have a moderate cost to it. You have to replace the entire basically thermal piping network that is that steam network. So it's relatively disruptive. There's a lot of construction involved. And generally, we think probably the earliest that could be implemented is around 2036 because of kind of the build out time for that. So what that means is you won't start seeing carbon emissions savings right away until you're actually able to implement the solution. We've seen this be successful on other campuses. Electrification is kind of the preferred pathway for a lot of stakeholders. We see it as being, highly viable from a political, community, and a technical perspective. But again, that implementation takes a while. There will be some disruption. And even within facilities, there's some disruption because certain facilities that are tied to the steam network now might have to have, mechanical or HVAC equipment replaced within the building as well. So there'll kind of be this gradual process of getting the campus ready for this new all-electric central plant system. So what does that look like in terms of emissions reduction? So this graph here shows that, again, that starting in yellow and kind of that top part of the graph, that's your business as usual case, what emissions would look like with growth. And then the two blue sections on the graph show the emissions reductions from different measures in our scenario. So this is currently a carbon glide path or a wedge diagram. And you'll see that 90% threshold there at the bottom. So in the year 2036, when the all-electric central plant and the new thermal network can be built out, you'll see a massive immediate reduction in Scope 1 emissions. I should mention the cogen plant in this case would still be maintained, but just as a backup resource. So you can still be islandable and have some of that resiliency that Nurit was talking about. But you won't be burning fossil fuels on a daily basis. So you'll see very rapid reduction. The dark blue part at the top is from that off-network electrification. So that's what the decarbonization measures at building assets that are not connected to the main campus network that I was speaking about. So heat pump replacement projects and things like that. So again, the goal would be met in the year 2036, and you'd have a very substantial reduction between now and 2045 in terms of carbon emissions reduction. Another scenario category here that's been getting a lot of buzz if folks have been paying attention to sustainability news and the Inflation Reduction Act. This would be tapping into what people are projecting to be a new kind of green hydrogen economy. So we would be converting the cogeneration plant that's running on natural gas right now to a hydrogen cogeneration plant. So you would be burning hydrogen in a new hydrogen boiler and with new hydrogen turbines to produce, again, still power, steam, and chilled water. So the advantage of this is that you can maintain a lot of the cogen plant. It's kind of a like-for-like replacement to incorporate hydrogen. You still have that islandability. You don't have to replace the steam network. That can stay in place. Although we do have sub-scenarios where maybe you want to convert that to a hot water network to potentially save some energy. But so the primary challenge with this is that it is dependent on hydrogen arriving on campus and truly being green hydrogen. So that's hydrogen that's produced with 100% renewable energy. So in our conversations with SoCalGas, they intend to be providing hydrogen to this part of LA and to campus by around 2045. But it is somewhat a risk in terms of focusing on hydrogen as your solution. As this is a new economy, new hydrogen distribution and production that needs to be developed, over the next 20 years. But if it arrives as promised, then it does have a certain appeal to it. So again, slower to implement, fairly low life cycle cost, not a lot of cost between now and 2045 when the hydrogen arrives. You also would not be adding a bunch of additional electrical demand to the grid, which means LADWP, the utility, who's working very hard to increase renewable energy on the grid and decarbonizing their own grid. That new power, all those new resources could go to other developments in the LA community instead of the UCLA campus. So that's one advantage. But there definitely is that risk of hydrogen not materializing or not being green, or kind of counting on new technology and new markets to pencil out. And here's what that emissions reduction wedge diagram looks like. So the primary difference you'll see here is relatively small amounts of emissions reduction until the hydrogen arrives in 2045. So the overall emissions in the next 20 years is closer to the business as usual, but once that's there in 2045, you would be well below that 90% emissions reduction target. And your annual emissions in the year 2045 would be about 1% of what they are currently. So still very effective, but takes longer to implement and less savings in the intervening time. Another interesting technology is a hydrogen fuel cell. So also using hydrogen from a new hydrogen pipeline, but instead of combusting that hydrogen fuel at the cogen facility, you would be using a fuel cell, which is an electrochemical process, but still would be producing power as well as hot water and chilled water. So it's more efficient than a combustion-based trigeneration facility, but it is also higher cost because it's less of a like-for-like replacement. You also would be looking to or required to replace the steam network with a new hot water network. So that's part of the additional costs as well. You're still tied to a very similar implementation timeline because we have to wait for the hydrogen to be available. On the graphic here, you'll see this approach for the fuel cells is showing, instead of just one central plant at the cogen, what we call a nodal plant configuration. So there would be 6 fuel cell plants distributed around campus. There's a number of reasons for doing that. Part of that is available real estate and where we would be distributing to. It's also a little bit more resilient to not have all of your eggs in one basket. So you've got several different kind of islandable parts of campus that can produce power, hot water, and chilled water directly. And one other interesting advantage of the hydrogen fuel cell is it actually produces more water than it consumes. So you would have a kind of net positive water resource that could be used for other things like irrigation or things like that. So again, similar graphic to the other hydrogen scenario in terms of when those emissions land. It's kind of waiting for that hydrogen to arrive, but then once it does, you're in a very, very low carbon operating state out in 2045. And again, this case still has the off-network electrification projects included. Another scenario category and option is relying on carbon capture. In this case, we're looking at also a fuel cell, but this would be a natural gas fuel cell or a methane fuel cell, which is a kind of more popular technology now because there is a lot more methane that is available. Of course, methane is a fossil fuel, and even though you're not combusting it in a conventional methane fuel cell, you are still emitting carbon dioxide as part of that process. But since it's not combusting that methane like we are at the current cogen facility, but kind of separating that methane into its constituent chemical parts directly, it is easier to do carbon capture than in a post-combustion configuration. So you can get pretty efficient and more effective carbon capture, although that still is definitely a pretty emerging technology. So you really are relying on the carbon capture to see that emissions reduction. And then there's also the question of what do you do with the carbon that you've captured? So you kind of need to develop a market or some retail partners for using that carbon and make sure that it stays sequestered and that it's not re-emitted into the atmosphere. So For example, if you were to sell that carbon dioxide to PepsiCo and they were to put it into their soft drinks, and then you open your can of soda and then it goes back into the atmosphere, versus putting it into say low carbon concrete. So there's a lot of developments in building materials that can use sequestered carbon and store it in those materials for a long time. So could be some interesting opportunities for applied research here, or pilot programs for using sequestered carbon in different products, but it's something that would have to be well thought out and developed to make sure all those emissions are real and long-term. This configuration for the methane fuel cell would be a centralized fuel cell. Doing the nodal configuration with several different carbon capture systems would be quite challenging to operate. So we're staying within kind of the existing cogen facility footprint. It is still very resilient and water efficient. It would allow you to island on campus the way you are now. It does come also with a fairly high life cycle cost because of the cost of the fuel cells. You still would be purchasing some power from the utility as well. And then there is the hope that, and kind of long-term planning, that you would be able to implement this earlier than the hydrogen scenario because you already have natural gas coming to campus. So this could probably be implemented by 2036 as well, similar to the all-electric central plant scenario. And then there's the hope that eventually you would be able to convert those fuel cells to hydrogen fuel cells and use the rest of the infrastructure that you have. So when that hydrogen market does develop, when technology continues to improve, you could make the transition beyond 2045. So you'll see here the big difference is in terms of this carbon emissions reduction pathway is how soon those emissions reductions can be realized. So that gold section there represents a 2036 implementation date for that fuel cell. You get very, very close to that 90% emissions reduction target as soon as that strategy the fuel cells are installed, depending on the exact efficiency of the carbon capture system and how far you are along the way of your kind of off-network electrification projects. But by the end of the project, once the rest of the off-campus electrification has been complete, you would be well below that 90% reduction threshold. While it is still connected to natural gas, your annual emissions in the year 2045, which is kind of the end of our study period, would be marginally higher than our all-electric scenario, which essentially has zero fossil fuel being burned at the central plant, and we would still have a little bit of inefficiency in terms of that capture technology. Okay, we ran through those pretty quickly, and we'll have time for questions at the end. So if you need me to clarify any of that, I'm happy to do it. There are, as I mentioned, we kind of have these larger scenario categories, which I've covered here, but then we also have several sub-scenarios. So we don't need to go into full detail on all of these, but I think the primary thing to mention here is that given that some of these technologies and solutions require a while to implement, we are very cognizant of kind of the timeliness of the climate crisis and the value of reducing emissions in the near term. So we've added scenarios that we're calling our accelerated scenarios. So for instance, the all-electric central plant can't be implemented until 2036. That's about 12 years from now. Something that could be done in the intervening years would be to keep the steam network operating while you're doing your planning and while you're installing the new thermal network for lower temperature all electric heating. You could install an industrial steam heat pump and produce all of that steam for campus electrically. So that technology exists now, primarily in industrial applications, but is being more commonly used in this kind of replacement application. It's less efficient than an all-electric central plant, but it could be deployed sooner because it's a simpler install and can use that steam infrastructure. So that would be one option for decarbonizing as quickly as possible while you build out your kind of preferred end solution. And then when that's ready to turn over, then you take the steam heat pump offline. Some other kind of sub scenarios that we're considering, another acceleration option for the hydrogen cogen scenario would be to install a carbon capture on the existing cogen facility basically as soon as possible. So that would be a little different than the carbon capture technology we talked about in scenario 6, which is off the fuel cells. So that would be a post-combustion carbon capture, which is essentially stripping the carbon CO2 emissions out of the exhaust stream from the cogen facility. That technology is also fairly new, but it could be an interesting place for some applied research as well, and trying to decarbonize sooner while your preferred scenario is under development. So those are examples of some of our sub scenarios that we are analyzing. And so at the end, this comes back to our multi-criteria decision analysis framework. So this is a little sample view of what our final scorecard will look like when we've completed our study. You'll see across the top, we actually have 14 criteria as well. So they are life cycle impact, greenhouse gas emissions, which I should mention, obviously the scope 1 emissions reduction and that 90% target is the primary project goal, but we also wanted to consider scope 2 emissions impact, from which scope 2 is related to indirect carbon emissions. So as a result of the energy that you're purchasing, the electricity off the grid as well. So we'll be analyzing that impact, as well as the impact to campus water consumption, the reliability of the systems, the resiliency. We talked about the ability to island and things like that. The environmental and climate justice impacts of deploying those solutions, which we're working with a local partner to develop those, as well as supply chain equity, workforce equity, political viability and community viability, kind of a risk and unintended consequences analysis, as well as costs, which we mentioned is both capital cost and operations and maintenance costs, disruption to campus, and the speed of implementation. So those are our 14 criteria that we're scoring our scenarios on. So when we release the final report, we'll be able to compare them across those metrics and make a final decision. All right, that's the content we have for now. Throw it back to Nurit for some questions.
Remember, you can use the Q&A. Do any of these options help us preserve the islanding capability? Gideon, would you like to speak to how you're addressing resilience and reliability in some of the new scenarios?
Yeah, great question. So if we think about the all-electric solution, a major challenge of that particular solution is that the campus could lose some of its energy system resilience because it's more subject to the potential for blackouts and brownouts in the local area. The campus can partially island currently because of the power generation capacity of the cogen plant. It's been agreed that for those all-electric solutions, the cogen plant is going to be retained essentially as backup power in the event of grid failure. So that does mean that the campus will be able to island to the extent that it already can. The cogen plant can't generate all of the campus's power needs, so it can't completely island, but it can to some extent, and that capacity will be retained in those scenarios where the cogen plant is removed and replaced with an all-electric option.
Thank you, Gideon. And in terms of the campus in the current scenario and in those scenarios, The cogen plant capacity is not equal to the entire campus, but we have what's called a load shed program. So the system automatically takes offline buildings that have less critical function to ensure that the critical functions of the campus are retained. Other questions? And feel free to share comments in the chat as well if you'd like us to record your feedback. And we'll also, as I mentioned, be sending out a document and survey as another way of collecting input, but happy to answer questions while we are here today. What are the main considerations besides cost for determining which way to go? Can you go back to the scenario criteria, please? So WSP is using a multi-criteria decision assessment framework. So basically looking at many different factors, including greenhouse gas emissions, water use, reliability, resilience, climate justice considerations and equity considerations, supply chain equity, workforce equity as part of that, political and community viability, so getting input from our stakeholders, risks and unintended consequences, cost, disruption, and speed. So all of these criteria will be presented as an evaluation framework to campus leadership to consider in selecting the scenarios. But you're certainly correct that cost is a major factor, and we will have to find a funding and financing pathway for this as well. All of the campuses are completing these studies at the same time, which we hope will enable some more cohesive approach to financing or funding in approaching the state or other or federal or other entities where we might be able to receive funding that will be really looking at the big picture of the University of California. Other questions? Could you talk more about the accelerated implementation scenarios? Gideon, that would be to you or your team, if you'd like to go back to that slide and talk about what that really means to try and have some accelerated options added.
Sure. Although, and Zach, you may want to jump in here, but I'm going to go past those, the list of scenarios, because I don't think that's useful. We could go back to the all electric scenario. So in this case, the central plant and the hot water network would be fully built out and operational around the year 2036. In the intervening years, the way to reduce the Scope 1 emissions to the 90% goal is to find a solution for supplying the campus with steam that doesn't involve the combustion of natural gas. And so the way that that happens is to take the cogen plant offline, retain it for backup, as we discussed, but to install a large heat pump that's capable of producing steam. That heat pump would be run electrically, and it would essentially be plugged into the steam network and replace that part of that function of the cogen plant. So that steam, that electrically powered steam producing heat pump would operate from about the year 2030 until the all electric central plant is able to come online, and that reduces those carbon emissions over that intervening period of about 6 years.
Thank you. Is adding additional renewable generation throughout the campus an option, such as increased solar, or is that only useful on a larger scale? Excellent question. So UCLA is already planning to add as much solar as we are able. So we did a full study of all eligible sites on the main campus and identified different parking structures and rooftops that would work for solar. Some are ineligible due to the roofing type or seismic considerations. And we did an RFP and selected a firm, Nextera. We have contracts for some of the first sites and are in design currently. So there will be a lot more on-campus solar coming in the next years to come. So we are trying to maximize on-site generation. But the density of the campus as an urban campus with very significant energy loads from laboratories and medical space, it's not possible to meet our total need with on-site solar. So we do have off-site as well, but we are prioritizing first the on-site. We're actually doing the on-site solar through the feed-in tariff program with LADWP, so it is not behind the meter, it is part of the grid, but we are trying to contribute our space towards maximizing in-basin solar. And let's see, it looks like another question popped up. Will the on-site solar also have battery storage as well? I do not think that we have any planned at this time. Because the solar is a very small percentage or relatively small percentage of our total need, there won't be excess solar generated. So there isn't really a need for battery storage, although battery storage may be utilized in the overall campus energy strategy. Is there an option for thermal storage for increased resilience? So FYI, UCLA does have some thermal storage already. We have a 5 million gallon thermal energy storage unit under Lacrette's Hall that is a chilled water based thermal storage. But I'll let Gideon or team answer whether there's any thermal storage under consideration. We do have a pretty crowded underground in this very dense urban campus. You know, just for those who may not have thought about our density much, some of our sister campuses like UC Davis are 4,000 acres. We're dealing with 419. So we do have a lot of space underground that is already taken up by utility infrastructure and others. But again, back to the consultants as far as any thermal storage potential.
Yeah, thanks, Nuri. I appreciate the question. We should actually have thermal storage marked on here. So we're going to update this diagram to show that the all-electric solution does have thermal storage built into it, because just to dive into I guess another layer of detail, this all-electric central plant uses heat recovery chillers that can simultaneously produce heating and cooling, and we can utilize thermal storage to absorb excess heating or cooling when it's generated, and then when it's needed, direct that to parts of campus where it's needed. So thermal storage is a good idea in terms of efficiency, as well as providing some additional resilience buffer. That is part of the all-electric solution. And as Narit mentioned, there's limited space on campus. So actually the limiting factor when it comes to sizing that thermal storage is what's available in terms of space to install that thermal storage. But it is an important part of the all-electric solution.
Thank you. Is UCLA Health and Labs doing their best on energy intensity and efficiency? I would say they are definitely actively working on these issues. I think there's more that we can do, especially in the lab space. But UCLA Health does have a dedicated energy manager and a sustainability team, and are working on energy efficiency and upgrades, retro commissioning, et cetera. So there's a lot of work there. I think the team is doing their best given capacity and staffing and resources, but could we do more? Of course, we can continue to do more, and we'll continue to push for continuous improvement. Thank you. Are there thoughts about implementing the invasive work of replacing steam and hot water? It will require incredible management and construction resources. That is definitely a major consideration, and within our scenario criteria, disruption and construction are a big piece of that. So we are definitely considering that as we evaluate these criteria, or as we evaluate these scenarios. Other questions? And again, we'll be sending out a draft soon for some input with sort of a status update of some of the deliverables that are still underway and a bit more detail on these scenarios. So we look forward to any feedback that you have. The final study needs to be delivered to UCOP in July, and then it will be for consideration of campus leadership, and about by the end, I think, of 2025 is the deadline for developing our plan and what we will do with these scenarios and how the campus will move forward to achieve these goals. So just in terms of timeline. Any other questions? Are these scores accurate or only placeholders? Those scores that were on the screen are pretty well along, so they may change in the final a bit, but they're not just placeholders. They do represent sort of the analysis so far. There are some on the equity side that are still TBD and still being developed, but the ones that are showing are not likely to change dramatically. They might adjust a bit. Other questions? And while you're thinking about that, I placed a couple links in the chat. One to an article about UC's new climate goals, so you have that background, and then also the decarbonization study page. So we'll be posting the recorded town hall there. We had 2 town halls today. I'm going to take the presentation from tonight, but I'll also tack on the questions that were asked earlier so people can see the answers to those. And then in the coming weeks, we'll be sending a Bruin post to the campus with a draft study and a survey for feedback. So you'll have that opportunity to give input as well. And of course, as I mentioned, you're always welcome to email me. I'll put my email in the chat as well, and I can field any questions with our consultants if you don't think of them tonight. The study is advised by a decarbonization task force that includes faculty, staff, and students, which is mentioned on the website. But yeah, we welcome broad participation. What is going to be prioritized when making the decision, if some have similar numbers on the chart? I think ultimately, leadership will need to evaluate all of these different criteria. I do think cost will be a significant factor, but many of these other criteria are very important as well. So ultimately the decision-making will be up to the chancellor, the executive vice chancellor, and UCLA leadership in choosing a path forward. But input and feedback are certainly considered along with all the different criteria in this analysis. When will students get a chance to give public comment? So comment was welcome now through the town hall, but we will be, as I mentioned, and you may have written this before I said this, but I'll just say it again. We'll be sending out a draft of the study with a survey for feedback. And so that'll go out to the entire UCLA community, students, staff, and faculty. And we would very much welcome student comments. Again, there are students on the decarbonization task force that has been guiding the study, but we want broader input and would welcome that. When that is going out, I know both CalPERG and USAC are here tonight, and I would greatly appreciate your help. Students get a lot of emails, so even though it's a Bruin post, they may not pay attention to it. And if you can help signal boost that and encourage students to chime in, we would love the input. Other questions? Will community feedback be relayed to the chancellors and decision makers? Yes, absolutely. We will share both probably summary and detail of feedback from the survey with leadership. Thank you for that question. Anything else? I'm happy to stay if folks do have more questions, but I don't want to keep everyone if people don't. Are there graphics showing which UCLA entity is the most energy intensive? There are not. We are working on metering across campus that will help us track at the building level. I can tell you offhand that laboratories and medical space are significantly more intensive than classroom space, for example. So we have a lot of, hospital, clinic, medical space. One fume hood, I don't know if any of you students are in, scientific wet lab type environments, but one fume hood can use as much energy as 3 to 4 houses. So the physical sciences, the laboratory environment at UCLA is very heavy energy use, and the medical environment as well. Thank you, Wes. I am so glad that this time was able to work for you. We wanted to make sure, I know students have a lot of different schedules, and staff do as well. And so we wanted to offer some other times. After we do the share the draft study and get feedback, we may also do an additional town hall before this study is over, but we wanted to kick off early, even though the study is still underway, and make sure to get input along the way. Do all options retain the cogeneration engines as a backup, or only the electrification options? I will hand it to Zach for that one.
Yeah, great question. So yes, it's primarily the electrification option. So the all electric central plant option, and there's kind of two different configurations of that. One is a centralized one and one is a nodal one, which we didn't really talk about too much. Those would maintain the cogen for islandability and backup, and we would just have to make sure to continue to maintain and run that facility every once in a while just to keep it at standby readiness level. And then the industrial steam heat pump scenario, which is also an electrification scenario, would retain the cogen facility as well. The fuel cell scenarios essentially provide that same resiliency, because they again can produce power as well. So you would not need to maintain the cogen facility in that case. And then of course the hydrogen cogen scenario is reusing a lot of that infrastructure, so that would be maintained as well.
Thank you. Yeah, excellent questions. When considering hot water versus steam efficiency, what are we saving by switching to hot water? Zach?
Yes, another a good technical question here. So the steam facility, or the steam network, inherently has some losses in it. So that was built, I believe, in 94, 95, or actually maybe earlier. Narit, was that before the cogen facility? I think there was steam.
Yeah, we were
infrastructure.
utilizing
Yeah.
steam about at least a decade before the cogen. That was before my time at UCLA, but we had a steam plant that was then replaced by the cogen. And I didn't mention this earlier, but we actually were really innovative in utilizing landfill gas early on. And so there was a biogas component to the plant, but that source of landfill gas, which was in the Sepulveda Pass, was a decreasing supply and decreasing quality, and we discontinued it in 2016. But that was a component of the cogen, so it was not all fossil natural gas during its operation. It also had some biogas.
Right. So
But
yeah,
yes.
so that aging steam infrastructure has some losses inherent to it. You know, some of that steam is coming out for process loads. There's leaking because it's a pressurized system, and then it's just a really high temperature. So there's more thermal losses through that network. So when you convert to a heating hot water network, you're at a much lower temperature. It would be new insulated piping. It's a fully closed network. So ideally, you're not providing much makeup water at all into that system. So we estimate that an aged steam system like that probably has thermal losses on the order of about 25 to 30%, which is pretty substantial. And a new network is just the thermal losses across insulation, so it's more like 7 or 8%. So there's just inherent heating savings from making that conversion.
Are you exploring other on-site energy generation beyond solar, micro wind, etc.? At this time, we do not have any plans related to micro wind. We're certainly always open to different technologies, but we do have a particularly dense urban campus that makes some of the on-site renewables not really practical. Zach, in the study, was there any consideration of micro wind as a complementary technology?
You know, we didn't talk about micro wind too much, given the challenges around real estate and just kind of in doing a lot of these studies before, just the density is very challenging to kind of make up a substantial portion of the energy demand. In your location, solar is really kind of the best distributed kind of rooftop scale solution. And like you said, you kind of already have a pretty detailed plan for deploying that. Yeah, you know, technically the We are producing electricity through the hydrogen scenario, so that's kind of production as well, although there's a difference in round trip efficiency because it takes electricity to produce the hydrogen, and then we're producing electricity from that, but it is still renewable and low carbon. The other one we considered was, looking more at biogas or anaerobic digestion as produced gas as a source of heating and electricity as well. But there wasn't good resources that were on the right scale to really serve the entire campus. So, but we did take a pretty deep dive on those options as well.
Appreciate it. I figured you had looked at it thoroughly, but yeah, my instinct was, given our density, it's where we are. There's a question about cost. I don't think all of the scenarios will be the same in cost, but if they were, the question is there a concern about the timing? I can't say there would be no concern about time and availability of funding and financing. A major next step will be looking at funding possibilities. The UC system is undertaking this all together because it also gives us a better ability to communicate the need for support from the state or pursue grants together, federal funding. So the financing and funding will be a major component of this. But I think if the scenarios, hypothetically, if the scenarios all cost the same, I think we would be looking to other factors like construction, disturbance, reliability, all those different scenarios that are being evaluated to compare more than the timing of the funding availability.
Yeah, and our preliminary financial numbers are showing that there is definitely a range of costs. And we're trying to paint a pretty complete financial picture, looking at that operating cost, when the cost for new construction would land for the different projects, because they have different development timelines, and kind of looking at the total cost of ownership across those systems to account for those differences. So there will be variation in costs for sure.
Thank you. Any other questions? Sorry if this was mentioned, but does the cost analysis include savings from decarbonization? Yes, the cost analysis will be looking at everything: upfront capital cost, long-term operational cost, savings, including reduced carbon compliance costs. So we currently are part of cap and trade, and we have to pay allowances based on our carbon production. So all of that will be taken into consideration. Thank you for asking. Okay, then I think we will close for tonight. But again, you're welcome to email me and get in touch. And as we have some student leaders here tonight, we'll definitely appreciate your support in getting this recording, draft study, survey for feedback, etc., out to the broader student community so that we hear from lots of voices with any questions, concerns, or feedback on the study. I know, by the way, we are already aware that there's a USAC resolution calling for 2035 if feasible, and that's a major priority for CalPERG. And so leadership will certainly be made aware of those broad voices, but we welcome individual input and feedback as well. Okay, I'm going to stop the recording.